For over 100 years, a mysterious cosmic object has been hiding in plain sight, captured in photographic plates from the late 1800s, decades before humanity even conceived of black holes. This celestial anomaly has been watching us watch it. The object is OJ287, a quasar located 5 billion light-years away in the constellation Cancer. But what astronomers have just confirmed about this ancient puzzle changes everything we thought we knew about the universe's most violent cosmic phenomena. The question we must ask isn't just what this discovery reveals, but what took science so long to see what was always there. In 1982, Finnish astronomer Aimo Sillanpää noticed something that didn't make sense. OJ287 wasn't behaving like a typical quasar. Instead of maintaining relatively stable brightness, it pulsed with an eerily regular rhythm, a 12-year cycle that suggested something far more complex than a single supermassive black hole devouring material. Think about that for a moment. A cosmic object 5 billion light-years away, photographed before we knew what it was, suddenly revealing a pattern that defied our models. Sillanpää proposed the unthinkable: two supermassive black holes, locked in gravitational embrace, orbiting each other in a cosmic waltz that produced these brightness fluctuations. But here's where the investigation deepens. For 40 years, hundreds of astronomers monitored this object. 40 years of observations, 40 years of data collection, 40 years of building mathematical models and predictions. The scientific community knew something extraordinary was happening, yet the definitive proof remained frustratingly out of reach. Why? The answer reveals as much about the limitations of our technology as it does about the nature of scientific discovery itself. Traditional telescopes, even our most powerful optical instruments, couldn't resolve the mystery. From Earth's perspective, OJ287 appeared as a single point of brilliant light. The two black holes, if they existed, were simply too close together and too far away for any ground-based telescope to distinguish between them. It's like trying to see two fireflies dancing together from 5,000 miles away. This is where the conspiracy of technological limitation meets the reality of scientific advancement. We've been observing this object for more than a century, but only when we combined Earth-based radio telescopes with the Radio-Astron satellite, a Russian space telescope operating between 2011 and 2019, did we finally gain the resolution needed to see the truth. Radio-Astron's orbit extended halfway to the Moon, creating a virtual telescope with a baseline that gave astronomers a view roughly 100,000 times sharper than typical optical images. 100,000 times. That's the difference between guessing and knowing. But here's the uncomfortable question. What else are we looking at right now that we simply don't have the tools to properly see? When the radio observations were finally processed and compared with theoretical calculations developed over decades, the evidence was undeniable. There, in the radio wavelengths, were two distinct bright spots, exactly where the models predicted the black holes should be. A third bright spot revealed the jet of material being ejected from the smaller black hole, twisted like water from a rotating garden hose as it whips around its larger companion. This isn't just confirmation of a scientific theory. This is visual proof of something that reshapes our understanding of galactic evolution. Binary supermassive black holes aren't theoretical anymore. They're real, they're observable, and they're probably far more common than we previously imagined. Consider the implications. If two supermassive black holes can orbit each other for billions of years in a stable configuration, it means galactic mergers, the violent collisions between entire galaxies, don't immediately result in black hole mergers. Instead, these gravitational monsters can circle each other for eons, creating the kind of regular patterns that Sillanpää first noticed in 1982. The smaller black hole completes its orbit every 12 years. 12 years. In cosmic terms, that's astonishingly fast for objects of such immense mass. As it orbits, the jet emanating from it appears to wag back and forth like a cosmic tail, a phenomenon researchers can now observe in real time. This gives scientists an unprecedented opportunity to watch the choreography of gravitational titans as it unfolds. Let's investigate what this discovery tells us beyond the headlines. First, it validates decades of gravitational wave research. Since 2015, instruments like LIGO and Virgo have detected the gravitational waves produced when black holes merge, providing indirect evidence that binary black hole systems exist. But OJ287 offers something different. Direct visual confirmation that these systems can remain stable for extended periods before their final merger. Second, it confirms that our mathematical models of extreme gravity are remarkably accurate. When researchers compared the new radio image with theoretical calculations, the black holes were positioned exactly where the equations predicted. This isn't just a win for observation, it's a validation of our understanding of Einstein's general relativity in some of the most extreme conditions in the universe. Third, and perhaps most significantly, it demonstrates that amateur astronomers with private telescopes can observe the same quasar that contains these monsters. OJ-287 is bright enough to be detected by dedicated hobbyists, meaning the evidence has been accessible all along. The democratization of this discovery is profound. You don't need a billion-dollar space telescope to participate in cutting-edge astrophysics. But this discovery also raises unsettling questions that demand investigation. If OJ-287 has been observable for over a century, and if its regular brightness variations have been documented for 40 years, why did it take until 2024 to capture definitive visual evidence? The answer involves funding, international cooperation, satellite lifespans, and the complex politics of space science. Radioastron, the Russian satellite that made this breakthrough possible, ceased operations in 2019. Its data took years to process and analyze. The research paper confirming the binary black hole system was finally published in October 2024 in the Astrophysical Journal. That's a 5-year gap between data collection ending and confirmation being published. In an era of rapid scientific advancement, that timeline reveals the glacial pace at which space science sometimes progresses when it requires extraordinary international collaboration and computational resources. Here's another question worth investigating. How many other quasars exhibit similar periodic behavior that we've dismissed or failed to recognize? If one binary supermassive black hole system exists, logic suggests there should be many more. Are we looking closely enough? Do we have the resolution we need? Or are we constrained by the same technological limitations that kept OJ-287 secret for so long? The black holes themselves remain invisible, perfect absorbers of light and matter, but they reveal themselves through their effects, the particle jets they produce, the glowing accretion disks of superheated gas spiraling into their gravitational wells, the way they twist and distort the fabric of space-time around them. The smaller black hole orbits the larger one every 12 years, carrying its twisted jet along with it. Over the coming decades, astronomers will watch this jet wag back and forth, a cosmic lighthouse sweeping across the universe. Each cycle provides new data, new measurements, new insights into how these systems evolve toward their eventual merger. Because make no mistake, these black holes will eventually collide. Their orbital dance is gradually decaying, losing energy to gravitational waves that ripple outward through space-time. In millions or billions of years, they will spiral together in a final catastrophic merger that will send gravitational waves powerful enough to be detected across the universe. When that happens, a new, even more massive black hole will be born from their union. This discovery represents more than just a pretty picture or a scientific curiosity. It's confirmation that the universe operates on principles we can understand, that our mathematical models correspond to reality, and that patient observation combined with advancing technology eventually reveals truth. But it's also a reminder of humility. We photographed OJ-287 before we knew black holes existed. We observed it for 40 years knowing something strange was happening. We built elaborate models and predictions, and only now, with the right tools and enough international cooperation, have we finally seen what was always there. The universe doesn't hide its secrets out of malice. It simply requires us to develop the vision to see them. OJ-287 has been broadcasting its binary nature for billions of years, long before Earth existed, long before humans evolved to look up at the stars. The cosmic dance was always happening. We've only just learned how to watch. As you look up at the night sky tonight, remember that somewhere in the constellation Cancer, invisible to your eyes but observable with the right instruments, 2 supermassive black holes are locked in gravitational embrace, circling each other in a 12-year waltz that began before our solar system formed and will continue long after humanity is gone. The question isn't just what else is out there waiting to be discovered. The question is, what are we looking at right now that we still don't have the tools to properly see?